Hello, my name is Amirreza Ashurian,
And my name is Artem Fedorov.
and we will be presenting our review of the Windows anti-kernel evolution from Windows XP to Windows 11. This presentation summarizes 2 decades of kernel development, major architectural changes, and the security and performance shifts that shape modern Windows systems. The anti-kernel uses a hybrid design that combines microkernel modularity with monolithic performance. Critical services run in kernel mode while staying modular, helping Windows balance performance and stability. Windows XP was designed for single-core CPUs, limited RAM, and a weaker security landscape. The rise of modern threats and multi-core processors forced a kernel redesign. Vista became the turning point with major security, driver, and performance improvements. Windows 7 and 8 built on Vista's foundation, refining reliability, performance, and security to meet evolving hardware and software demands. The hybrid NT model has remained consistent for decades. Fast kernel mode operations with modular internal structure. User mode runs applications and compatibility layers like WSL, ensuring crashes stay isolated. The executive layer handles resource management, I/O, security, and memory at the kernel level. The kernel manages scheduling, interrupts, and synchronization. The HAO abstracts hardware differences so Windows can run on x86, x64, and ARM architectures. Security evolved from almost non-existent protections in XP to hardware-rooted virtualization-based security in Windows 10 and 11. Key additions include UAC Secure Boot, Credential Guard, and TPM 2.0 enforcement. Scheduling evolved from simple single-core logic to advanced multi-core, NUMA, and hybrid core optimizations. Memory evolved from superfetch to memory combining and compression. NFTs gained stronger integrity and security features. REFS introduced resilience. Windows 11 added direct storage for direct NVMe to GPU data paths. Virtualization became a security foundation. Hyper-V, VBS, and WSL2 show how isolation became central to Windows system design.
Overall, Windows transformed from a compatibility-driven OS to a security-first, hardware-integrated platform. TPM ensures measured boot and hardware-rooted integrity before the kernel initializes sensitive uh, subsystems. Windows 11 enables VBS by default using Hyper-V protected memory regions for conditionals and code integrity. Hybrid CPUs require intelligent scheduling. Windows uses telemetry like Intel Thread Director to place workloads optimally. Direct storage bypasses legacy I/O overhead, allowing NVMe SSDs to communicate directly with the GPU. Modern Windows blocks vulnerable or outdated drivers by default, reducing kernel attacked surfaces. Windows shifted from minimal software security to a proactive. Windows shifted from minimal software security to a proactive, isolation-based model anchored in hardware trust. Scheduling now relies heavily on OS hardware core design to manage diverse execution contexts effectively. SSDs required a complete rethinking of I/O design, leading to advanced caching, parallelism, and NVM to GPU uh, pipelines. Because the kernel is closed source, research depends on documentation, system behavior, and academic analysis. The anti-kernel's evolution demonstrates real-world OS concepts. Future directions include confidential computing, stronger virtualization, and heterogeneous scheduling. Thank you for watching.